as stated, we are going to score each of our three models according to their accuracy. As we've discussed before, it's actually the validation accuracy, or in other words, the accuracy on the validation set that we will use to select each of our models. But first, let's just start by calculating each model's accuracy on the training set. So we'll start with model 1, which is the logistic regression model. Now, here I'm actually going to calculate the accuracy somewhat manually. But later on in this video, I'm going to show you how to use a particular tool from scikit-learn to calculate this accuracy a little bit more quickly. Okay, so to calculate the accuracy according to the logistic regression model, we start by generating predictions for the training set. So I'm going to take xtrain, provide it to predict, to the predict method of model 1. So this will create predictions for the training set. Recall that the training set contained 480 rows and 4 columns. So it contained information for 480 different flowers. So this predict method will generate predictions for each of those 480 flowers. We're going to store those predictions in what will be a one-dimensional array with 480 entries, and we'll call that mod1 predict train. So these are just the training predictions according to model 1. I then need to compare those training predictions to the actual predictions. I need to compare the predicted labels to the actual labels. So when I perform this comparison, the result I get will be a Boolean array with 480 entries. That Boolean array will contain a true for any observation where the predicted label is equal to the actual label, and it will contain false for any observation where the prediction was not the same as the actual label. Okay, so if I want the training accuracy, what I would need to do is sum up all of those Boolean values. That would effectively count the number of observations where there was a true. And then I would divide by the total number of observations. So I could do np.sum of this Boolean array, and then divide by the total length of either of these two arrays, effectively dividing by 480. However, a shortcut for that would be to use np.mean. np.mean does exactly what I just described. It would sum up the elements and then divide by the overall length. So if I run this code, that will it'll calculate the training accuracy and store the result in a variable called mod1 training accuracy. And then I will print that out, and I see that the logistic regression model got a roughly 97% accuracy on the training set. Okay, so let's see how well the decision tree model and k-nearest neighbors model did on the training set. Okay, so here I'm following essentially the exact same process. I'm taking the training data, providing it to the predict method of the decision tree model, and then I'm storing those predicted labels for the training set. I'm then comparing the predicted labels for the training set to the actual labels. I'm getting a Boolean array. I take the mean of that Boolean array, which will give me the training accuracy for the decision tree model. And then I print that out, and I get 1. So the decision tree model actually gets a 100% accuracy on the training set. If I apply the decision tree model to the training set, it gets every single observation correct, 100%. Okay, so finally, let's consider the k-nearest neighbors model. So the code here is exactly the same as in the previous two blocks of code. The only difference is I swapped out the model for model 3. So I generate predictions for the training set according to KNN, and then I calculate the accuracy and then print the accuracy. And here I get 97.08% accuracy. So what I see is that logistic regression and k-nearest neighbors perform approximately the same. They get essentially the same accuracy on the training set. The KNN model gets a very slightly higher score on the training set. However, the decision tree model gets a perfect accuracy on the training set. For the training set, it makes perfect predictions. It might be tempting at this stage to pick the decision tree model as our final model, assuming that it will work the best. However, as we mentioned before, you should not use training performance as an estimate for how well the model will generalize to new observations. We will see in future lessons that decision tree models are actually very, very prone to overfitting. In other words, they can learn the intricacies of the training data so well that they do very well on the training data, but they come up with these overly complicated rules that don't generalize well to new observations. If we want to compare these models, what we actually want to do is calculate an out-of-sample. We want to measure their out-of-sample performance. We want to calculate their accuracy on observations that were not seen during training. Fortunately, we held out a validation set specifically for this purpose. So now let's calculate the validation accuracy for each of these three models. Okay, so we could calculate this validation accuracy using the same process that we did before. Generate validation predictions, compare them to the actual labels from the validation set, and then pass that to np.mean. Fortunately, though, scikit-learn gives us a more convenient tool for calculating accuracy. And that comes in the form of the score method. Every single model that you would create in scikit-learn has a score method that is used for calculating performance metrics. For a classification algorithm, it will output the model's accuracy. So, for example, let's say I wanted to calculate training accuracy using the score method. So here I'm calculating the training accuracy for the logistic regression model. So I'm taking the training set, xtrain and ytrain, and providing it to the score method of model 1. We'll see in a minute that this outputs the that 0.96875 number that we calculated previously. If I wanted the training accuracy for the decision tree model, I could call model2.score xtrain ytrain, and that's going to give us the 1.0 accuracy score that we had previously calculated. And then if I wanted the training accuracy for model 3, I would just call model3.score xtrain ytrain, and that's going to give us the 0.9708 accuracy that we had previously calculated. But if instead of training accuracy, I want validation accuracy, then all I do is switch out the training set for the validation set. So instead of xtrain and ytrain, I use xvalid and yvalid. So this will calculate the validation accuracy for model 1. This calculates the validation accuracy for model 2. And this calculates the validation accuracy for model 3. So we will calculate all of those and then print them out with some text explaining which is which. So what do we notice? Let's start with the logistic regression model. The logistic regression model gets a validation accuracy of 0.967, essentially, which is very slightly less than its training accuracy. That is not uncommon. It's expected, in fact. It's to be expected. Your models will typically, not always, but generally, they will perform better on the training data than they will on the validation data. That sort of makes sense. They will do better on the observations that they saw while they were learning than they will on new observations that they've never seen before. So it's not unreasonable to expect there to be a small difference here. The good news is that, at least for the logistic regression model, that difference is small. The validation score is actually really close to the training score. Let's compare that to the decision tree algorithm. The decision tree algorithm got perfect accuracy, 100% accuracy on the training set. However, it only got a 0.917 accuracy on the validation set. So as noted before, what's happening here is this decision tree model is learning really complex rules that allow it to do very well on the training set, but are in some sense very specific to the observations that were in the training set. So even though it does very well in the training set, it actually doesn't generalize that well to new observations. I mean, a 92% accuracy is not bad, but it's certainly not as good as the 97% accuracy we would get, validation accuracy we got with logistic regression. Okay. Finally, the KNN model got a validation score that was, again, slightly lower than its training score, but not much lower. And in fact, we see that the validation score for Model 1 and Model 3 are exactly the same, 0.967 roughly. So if we were going to use validation accuracy to select our final model, we could reasonably select either Model 1 or Model 3. They both have exactly the same validation accuracy. I will actually select, for this example, I'm going to select the logistic regression model. The reason for that is logistic regression models tend to be a little bit easier to explain. Like if you need to explain to somebody why the model is making the predictions that it is, then that's easier to do with logistic regression than it is k-nearest neighbors. We'll understand why in future lessons. Furthermore, logistic regression is a little bit more efficient to implement than k-nearest neighbors. K-nearest neighbors can be a very slow algorithm to use. So just for computational reasons, we might prefer logistic regression over k-nearest neighbors. So all else being equal, just looking at the validation scores, we could maybe pick either one of them. But as it turns out, logistic regression often has a few advantages over k-nearest neighbors. So we'll pick logistic regression. OK, so let's score our final model using the test set. OK, so here I'm going to calculate model1.score, and then I'm going to give it x-test and y-test to give us one final score on how well we expect this model to do on out-of-sample observations. So I run that, and I get a testing accuracy of 0.9, which is actually dramatically less than the validation accuracy. So our assessment of how well this model will perform on new observations is really only at about 90%.